So thank you very much for your introduction, and it's a pleasure to give the talk at this meeting, and many thanks to Professor Panigrahi who kindly invited me to give the talk. And this year we are celebrating 100 years of quantum mechanics. So it is a particular pleasure to give a talk at a meeting which is also commemorating this event. And first, let me indicate the outline of my talk. The first, since I think it's a mixed audience, and many of you may not be experts in the area. So I shall spend a major part of the talk in explaining the underlying motivation for this line of study and the current state of research. And towards the end, we'll discuss our very latest recent work, which has attracted much interest and which is being experimentally tested, which was published last year. The reference is mentioned here. And this work has been discussed in various places, and in the Scientific American article, our example was referred to as Schrödinger's pendulum experiment, the term which I shall use also in my talk. And my collaborators in this work have been Professor Shogoto Bose and Deborshi Das at University College London, and the experimentalist Henrik Ulbrich at University of Southampton, whose group is now conducting experiment on our proposal. In my talk, towards the end of the talk, I shall indicate only the basic idea of our proposal. Will not go into much details, its significance, and a bit on experimental feasibility. If there are questions about more details, I shall be glad to answer. So, 100 years, it is interesting that it is on 100 years back, it is in this month that Heisenberg's the first seminal paper on what we call quantum mechanics now. So my talk today will concern the line of studies inspired by Bell's theorem in 1964, which had really ushered in what may be called the experimental line of studies on quantum foundational studies. And this line of studies is now gaining increasing attention and interest and considerable effort. So we expect during the next phase of quantum mechanics in the coming years, after all these 100 years, there will be more experimentally oriented studies on quantum foundational issues. This is a significant break that has occurred after the discovery of Bell's theorem. Now, to motivate this line of studies, I first just quickly review, after 100 years of quantum mechanics, what may be listed as the most outstanding foundational issues. And interestingly, the line of work I shall be discussing in today's talk concerns about to what extent one can provide insights and perspectives on these issues from experimental point of view. So these are the three key issues, and I shall touch upon them in my talk. In particular, shall explain what the essence of what is quantum measurement problem, because many of you may not be aware of it the way the way. So this is quantum measurement problem, and this idea of testing quantumness of gravity by tabletop experiments, that is a fairly new idea. So I shall spend some time explaining what it is all about and to what extent the line of studies I am discussing is relevant. But first important point I want to make for addressing all these issues, as I shall now quickly explain, is important to test the validity of what may be called the quantum mechanical superposition of macroscopically distinct states of a macro object. While over the last 100 years, quantum mechanical superposition has been widely tested and exploited and harnessed and so on for microphysical systems, in the new era is now dawning where the quantum mechanical superposition will be harnessed for macro objects in the context of superposition of macroscopically distinct states which are macroscopically distinguishable. For example, in the ordinary double slit experiments and all those standard applications of quantum mechanics, superposition of microphysical systems are involved, and the states and the distinction between the states is also at the microscopic level. Now, for this line of study, the temporal version of Bell's inequality, which is known as the Leggett-Garg inequality, and I assume there may be there are quite a number in the audience who may not be aware of Leggett-Garg inequality because it is not yet now that widely known. So I shall spend some time explaining what is the basis of it, its motivation, and in what sense it complements Bell's inequality, which I assume all of you know very well, and the implications of Bell's inequality and so on. Now, to motivate these studies from the very basics and to put everything in proper perspective, and also to be able to distinguish between the implications of Bell inequality and Leggett-Garg inequality, let us start by defining precisely what is meant by non-classicality or quantumness, independent of the details of any theory. So what are the characteristic traits of any classical theory, essential traits of a classical theory? So these are the conditions that may be listed as the essential characteristic traits of any classical theory. And of this property of realism may seem to be very philosophical notion, untestable and so on. And yeah, but this notion of realism plays a key role in this whole research enterprise. And so that's why I've written clearly its definition. The concept of definite values of all the observable properties being assigned, even when they are not measured. So this is the notion we use in our everyday life and in the macroscopic classical world we live in. The notion of locality is well known. This is also a well-known condition. So let me spend a few minutes on this condition, which is that also in the classical world or for any classical theory, while the act of whatever way you model the process of measurement, in principle, you can always make the disturbance involved in the measurement process. By disturbance, we mean the extent to which the measurement process affects the properties of the measured system. This is the sense in which I will be using the term measurement-induced disturbance. The extent to which you affect the properties of the measured system. So the act of performing a measurement of disturbance that is produced by the measurement in principle can be made negligible in any classical model or classical theory or any classical viewpoint or interpretation. So the act of performing a measurement should have no influence on the subsequent properties of the system, at least in principle. You can assume that without any inner contradiction of arising within the theoretical framework, classical theoretical framework. Now, this notion of classical realism in itself is not testable. This is the famous Stephen Hawking comment, but it is interesting that this line of studies centered around Bell inequality and Leggett-Garg inequality provides a twist to this idea in the sense that the notion of reality is made testable provided it is combined with some other suitable condition. In the context of Bell inequality, hello? Hello? Hello, can you hear?
Yes, yes, we can hear you, sir.
Any problem?
No, 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 not at all, sir.
I heard something. So locality condition for Bell inequality, and in the case of Leggett-Garg inequality, it is non-invasive measurability. So this puts things in perspective, which I've already told you, and quantum mechanically predicts violation of Bell inequality, and it is well verified. As you know, the famous loophole-free experiments of 2015, and which got a Nobel Prize for 2022, and also the quantum technological spin-offs from Bell inequality, quantum information theory, the foundations-based information theoretic developments. So this you all know very well, but this is the new line of studies that has been emerging over the last 2 decades, I may say, although Leggett-Garg inequality was discovered in 1985, but for long it was ignored and not given the importance it deserves, and now its importance is being increasingly realized. And interestingly also, the Leggett-Garg inequality, which is the Leggett in jointly with his then postdoctoral student Anupam Garg. This inequality was inspired by Schrödinger's famous paper, Schrödinger's cat paper of 1935. And Leggett's motivation was to search for, as he put it in his papers of 1985, to whether one can get Schrödinger cat's laboratory cousins. That was the title of one of his articles during that period. Schrödinger cat, you all know. So what Schrödinger cat involves really is the paradox arising from applying superposition of macroscopically distinct states. The question that what one means by superposition of alive and dead states of a cat really stand for two macroscopically distinct states of a macroscopic system like cat, and alive and dead are two macroscopically distinct states. So for any macro system, for such macroscopically distinct states, whether one can apply quantum superposition principle, this was the question Schrödinger raised there, and he also in that paper said that it was necessary to apply quantum superposition for macroscopically distinct states in order to describe quantum measurement process. And this had inspired Leggett to search that whether one can provide means for experimentally searching for Schrödinger cat type systems in the laboratory scale. And I shall explain what this concept of macrorealism. It is conjunction of realism plus non-invasive measurability, which I've already stated those conditions. And so, while to put again things in perspective so that one can clearly see the distinction between these two lines of studies. A line of study testing local realism, a line of study testing macrorealism. So in this case, one measures correlations between properties of spatially separated particles in entangled states. The quantum entanglement plays a key role there, and its significance lies in illustrating holistic feature of quantum entanglement for macroscopically separated particles. On the other hand, the Leggett-Garg inequality-based studies, which are test of macrorealism, concerns importantly not concerns just a time-evolving single particle and correlations between results of successive measurements at different instants of time. And in the special case of the example we'll be considering in this talk, this time-evolving single particle will be taken to be a single oscillating particle like a pendulum. So it's a time-evolving single particle, and you are making measurements of its property at successive times, at different times, and the correlation between the measured results. Now, while in the case of Bell type study, quantum entanglement is involved. In this line of study, it is essentially quantum superposition principle applied to a single time evolving particle, which if it is a macro system, then it is superposition principle applied to a macro system. And application of superposition principle and computing such correlations entails measurement-induced disturbance. You all know the state updating is involved in calculating such correlations. So this is what I just now stated, and this is the point, important point. And so these are two distinct but complementary aspects of quantumness that are being studied. And these three lines of studies using the Schrödinger cat type studies, which are now employing Leggett type inequalities. One is for the experimentally oriented study of the measurement problem. The other, we are studying macrorealism versus quantum mechanics, and I shall explain that how in this kind of study Leggett-Garg inequality enables more stronger the test of realism than Bell inequality. This is an important conceptual point which I shall try to make clear, and of course it provides a key ingredient for testing quantum natural gravity. I shall spend a few minutes explaining why it is so. And then I will proceed to talk about what the Leggett-Garg inequality is and how it is derived and so far what experimental tests have been done. Now, the term quantum superposition principle, when we use, it is important to bear in mind that it involves two components, because otherwise in the classical theory also you have superposition principle in the sense of superposition of states, superposition of waves, superposition of in various contexts. But in quantum superposition principle not only involves superposition of states, but quantum superposition principle is empty, without of any consequence, unless quantum measurement postulate is used. Quantum measurement postulate gives meaning to what we mean by quantum superposition principle. And for this, it is necessary to consider quantum treatment of measurement. As now, the measurement, you verify quantum theory by measurements of properties of microphysical entities. But it is important to note that measurement of such properties necessarily involves macroscopic measuring apparatus. So to describe any measurement process, quantum mechanics has to be applied to this macroscopic apparatus and hence to massive systems. And that is the importance of, and that is from where the importance of testing quantum mechanics at the massive systems stems, which was ignored largely over the last 100 years, first 100 years of quantum mechanics. For a long time it was believed quantum mechanics should not be applied to massive systems, should not be applied. It's just ended. So now all these things over the last few decades, our notions have become more precise. And now the measurement process description, which was first given by von Neumann in his 1932 book, but largely remained unstudied, picked up studies from 80s again. So the result of such modeling of all measurement processes by quantum mechanics is that ultimately you get a combined state of system measuring apparatus of this form, where note that the psi1 and psi2 are the eigenstates of the observable of the microscopic measured system, while these capital phi's are the states of the measuring apparatus. And for the measurement process to be done, it is necessary that these two states of the measuring apparatus has to be macroscopically distinguishable. Otherwise, how can you decipher one outcome from another outcome? Outcomes different outcomes correspond to different states of the macro apparatus. But any quantum mechanical description of the measure interaction between the system and the measuring apparatus will result in a combined state. This is an entangled state, but entangled state between micro and macro systems. Then comes the important observation that this combined entangled state then automatically implies that change of the state of the measured system due to measurement process, which is technically called nowadays update of the state of the measurement system entailing measurement induced disturbance. It simply means that because that this is a combined state, so if you compute the properties of the measured system, it will be different from what the properties were before this interaction occurred. So the measurement process definitely affects the properties of the measured system. It has to affect because any question, please? Hello?
Hello, sir. Hello, sir.
Hello.
In slide 11, previous slide.
Yes.
Yes. System measuring apparatus combined states psi equal to A psi 1 cross phi 1 plus B psi 2 cross phi 2. In any experiment system, only A term will be there or B term will be there and C plus other term will be there.
No, you are making experiments on an ensemble of systems, measured system. Ensemble of. So sometimes I'm considering two-state system. So I'm considering measurement of a dichotomic variable property of that system. So there are two outcomes. So there are two possible states of the measured system. No, this psi 1 and psi 2 are eigenstates of the observable that is measured. So this psi 1 state is this and psi 2 this. Here observable alpha you are measuring is eigenstate. So the outcome is alpha 1 and alpha 2. And these two outcomes will correspond to the states of phi 1 and phi 2. How do you denote outcomes? You denote the outcomes from the state of the measuring apparatus, the pointer reading. So you may say this apparatus are really the pointer. Or sometimes people use the term system measuring pointer quantums, combined state. So it is the pointer states phi 1 and phi 2 corresponding to two different outcomes of measurement.
So
and
these
outcomes have to be distinguishable. So that's why this it has to be.
So it has to be only two then.
Only two because we are considering a two-state system measuring the
okay, sir. Okay.
You can always extend this, but I've kept, for illustration kept it simple.
Okay, sir. Thank you, sir. Thank you.
It's a good question. So
okay, sir. Thank you.
You are free to interrupt me and ask me because
okay,
because of the constraint of time, I may be skipping some points. So that
yes, sir.
But the important point is that whatever way the lesson we have learned about the various treatments of quantum measurement that have been discussed over the last few decades is that it is inevitable that system measurement apparatus interaction in various contexts should ultimately result in such an entangled state, and that will involve measurement-induced disturbance. But then the question is that how do you then explain, this is the important point, that in any single run you are observing a definite outcome. Different runs, different outcomes. But this description, the entangled state description, this is the question that is much debated. Is it sufficient to explain the occurrence of a single definite outcome in any individual run? Because a system measuring apparatus combined state is a pure state, entangled state, and it corresponds to a homogeneous ensemble. All the members of the ensemble after interaction quantum mechanically are described by the same wave function capital psi. This psi corresponds to the whole ensemble of system apparatus system. So it is homogeneous ensemble. Yet the measurement outcomes I talked about, they should be definite and distinguished. So it should be a heterogeneous ensemble. There is something about measurement outcomes missing in that description. But standard quantum mechanics does not allow a pure state to evolve into a mixed state. How does you explain the emergence of a heterogeneous ensemble at the end of a measurement process, where you can distinguish between different pointer states from which you can infer the probability of outcomes? So the probability of different outcomes which are given by Born rule can only be derived, inferred, if the definiteness of a specific outcome is distinguished from other possible outcomes. Now, how to ensure this within standard quantum mechanics is a question much debated, and various approaches have been discussed. I shall not go into the details, but the point I'm making is that for the purpose of the present talk and the work that I'm discussing, the important point to note is that the first part, that just to describe the measurement process quantum mechanically, you need to apply the quantum superposition principle at the level of apparatus as well. And that involves superposition of macroscopically distinct states for a macro system. Now, is the quantum mechanical superposition applicable for at the level of mass which is involved in any measuring process? So far, superposition principle has not been verified up to that level. Any further? That is a question further.
Excuse me. Yeah. Where do you define the boundary between microscopic state and macroscopic state? Is it clear boundaries there, or is it arbitrary?
No. That's the point. I'm glad you asked that question because of the constraint of time. In fact, this issue requires a bit elaborate discussion. So, first of all, the point is that the question I made is independent of what you mean by micro and macro, provided you assume quantum mechanics is a totalitarian theory. So prima facie, it should be applicable all the way from micro to what we call macro. There should not be any quantum classical boundary, micro, macro. Quantum mechanics must be applicable all the way. But the founding fathers of quantum mechanics, when the standard interpretation was given, first Bohr gave the dictum that no, the measuring apparatus has to be described classically. That was the original Copenhagen interpretation. But later on, then the other people came along, starting with von Neumann, David Bohm, John Bell, and so on, that the measurement, we have to consider application of quantum mechanics for the measuring apparatus as well, that in order to solve, to have a seamless description of our physical world, and also importantly to explain how a measurement occurs quantum mechanically, if assuming quantum mechanics is the theory, totalitarian theory. So now this is the approach I am adopting here. This is the approach people are trying to now study, to what extent we can then push quantum mechanics to the macro level, pushing the envelope of the validity of quantum mechanics to the macro level, which is essential for the inner consistency of quantum mechanics itself, because you make predictions on microphysical systems. What is a theory good for unless its predictions can be verified? But to verify predictions of quantum mechanics, you need coupling with macro measuring apparatus. Then it should be also described consistently within that theory. Now, that whether it fully consistently describes it, that is the point of debate. The first part is clear. If you describe it, you get that entangled state description, which ensures there is a state, if you assume superposition is applicable. But then still it does not explain it. This is the measurement problem, that because it is a pure state, how do you distinguish between different outcomes is not present in the theoretical description.
Dipankar, may
Yes.
I add one point here?
Yes.
As you beautifully explained that why actually what is the difference between this pure state and when we get the outcome, that is a heterogeneous ensemble of mixtures. So can you go to the previous slide? I wanted to say something. Yes, here. Actually, here, if we actually we can do measurement in any basis, right? So psi1 and psi2 is a particular orthonormal basis. Now I can actually take another basis, which is superposition of psi1 and psi2. Then I can express this state in a different form, where the apparatus part will also be in a superposition of capital phi1 and phi2. So then this superposition of macroscopic system will come, and that is somehow is little bit surprising in our real world. We don't see superposition of macro system or macroscopic system.
Yeah. That is the Schrödinger-Cat paradox. But before even going to that, even writing in this basis, we have a problem, because this does not describe the measurement process in its entirety for a observable whose eigenstates are psi1 and psi2. When you are rewriting it in terms of that thing, it is considering the paradox comes in a different way, that the same measurement can be looked upon as a measurement of another variable whose eigenstates are psi1, and that variable can be non-commuting with this variable. So you can then this formalism implies simultaneous measurement of non-commuting observables. This is a very serious technical objection. This is called preferred basis problem of the quantum. This is, and that people, it is not often stressed. So then Heisenberg's answered it. So this is why we say that within quantum mechanics, there is an inexactness, inner contradiction, unless measurement problem is addressed. But anyway, I'm leaving it there because the purpose of my talk today is not just measurement problem, but to stress that even to start, and nowadays, now it is becoming possible to study various approaches to this problem. The first stage in over the last 100 years was to establish that it is indeed a serious problem, because the traditional physics community tried to ignore this problem. But now, thanks to also Nobel Prizes in 22 giving importance to Bell's theorem and foundational aspects, and that has led to all technological spin-offs, people have started to taking foundational questions more seriously. So this measurement problem is also becoming important, and in this context, Leggett-Garg inequality is also becoming important.
Okay, thank you.
But there is a beautiful article by Weinberg in 2017 in New York Review of Books, and also appeared in Scientific American, about why he also considers the measurement problem to be the central problem. And also there are many other articles, but I'm not going into that. So now what is important is that Mr. Chairman, hello? Mr. Chairman of the session, hello.
10 minutes more, sir. 15 minutes.
Yeah, I know. That's why I called you. The way I'm going, so I will require a bit more time if you can please permit. Otherwise, okay.
Yeah, you can take more, sir. No, sir.
About a bit more. I thought earlier it was 1 hour time I have to give the talk. Huh? So because we are having questions in between, and that is good, questions in between. So, and this is okay.
So, time, sir. It's okay.
So now what important point is that there have been various solutions to the measurement problem proposed. The one line of study proposed that you preserve the mathematical formalism but modify the interpretation in any way. Because you cannot, if you preserve the mathematical framework of quantum mechanics, a pure state cannot evolve into a mixed state. Now, how can you interpret quantum mechanics in a way so that even if you preserve that standard formalism, you can ensure occurrence of a definite outcome, distinguished from other possible outcomes. There are two kinds of models proposed, which are, there have been many interpretations. These are the two major approaches. And the other line of approach has been that you modify the Schrödinger itself, that what is called, because the wave function notion collapse we all know from textbook, from undergraduate studies. But that is a very, this is the way wave function collapse was first introduced by Dirac in his famous book. But Dirac's statement of collapse that the system jumps when being measured to the eigenstate of the observable being measured is an inexact statement, because it ignores the role of the measuring apparatus. What does one mean? That is what John Bell had very emphatically said. What one means by system jumping into the way Dirac's collapse postulate was said, that you measure an observable and the system jumps to the eigenstate of the observable that is. It is very convenient for a beginner, and in those initial years of quantum mechanics, it was very useful strategy in order to get along, to see how the theory. So then John Bell and others came along, and David Bohm, they questioned it, and they said that it was meaningless to talk about the system alone. You have to take into account the measuring apparatus. And that was done, of course, by von Neumann way back in 1932 in the last chapter of his famous mathematical treatise on quantum mechanics, which unfortunately very few students read, which was to provide more mathematical rigor to Dirac's book. But in that book, in the last chapter, he described the measurement process in the way we discuss now. And all the models of quantum measurement have been inspired by the von Neumann model. There, von Neumann emphasized that the collapse thing has to be formulated in terms of a pure state going into a mixed state. And how can one ensure that? That in the recent years, by recent I mean from the late 80s and so on, approaches have been proposed. How can you introduce nonlinear stochastic terms to Schrodinger equation, which is negligible in the microscopic regime, that means for lower mass, for which standard quantum mechanics is well verified, but it introduces corrections at a large mass level, which hopefully can be experimentally detected. So it does not vitiate the tremendous empirical success we have of standard quantum mechanics in the micro world, but provides a way of describing the macro world quantum mechanically through nonlinear terms in Schrodinger equation, which becomes significant for large mass. So these kind of models have predictions about the breakdown of quantum superposition principle of macroscopically distinct states. In fact, that is the reason why the study of quantum superposition for macroscopically distinct states will lead to important empirical constraints on such models. To what extent you can modify Schrodinger equation. There is also the other approach. I'm not making any comment on that further. It will take up my time. I'm already running very short of time. So what we mean by experimentally oriented study of the quantum measurement problem is to provide empirical constraints on the model proposed for modifying. This is the very important point to note. And this line of study is becoming important, and we expect in the next 10 or 20 years, there will be some significant breakthroughs in the sense some of the models proposed may be ruled out, and of course it will be most exciting if some effects not captured by the standard quantum mechanics are empirically discovered. So by studying such models, and that's why experimental tests of quantums is crucial to provide these empirical constraints, and for this purpose LGI provides a tool. To give you an idea that already we have experimental ventures coming up. Recently there was this famous experiment, underground test of certain types of collapse models. Penrose's gravitationally induced collapse model. I'm not saying anything about it. I've already got distracted much, running short of time. But it is just for those who may be interested to note. And also another point, I just note that this is itself an interesting topic. Earlier, this Bohmian model I mentioned, the approach proposed to address the quantum measurement problem, was considered to be not testable. It has all predictions similar to quantum mechanics, but also the question of testability of Bohmian model is now becoming a topic of active studies in the context of arrival time distributions, kind of experiments where standard quantum mechanics fails to give unambiguous prediction. I'm not elaborating any further. Another area in which this question of quantum superposition of macroscopically distinct states of a macro system is becoming important is, of course, regarding the question of testing of quantum gravity. You all know this is the outstanding question, how to reconcile general relativity with quantum mechanics. But the important point, of course, there have been debates between the various models of quantum gravity, string theory, loop, the loop model, the gravity loop theoretic frameworks, but we lack any clear-cut direction how to discriminate between them. But also at the heart of the issue is also the question how one can test whether gravity is really quantum. So far, there has been no clear-cut experimental signature of quantum mechanical nature of gravity. Although theoretically, even in our usual classical world, the general relativity is known to lead to Newtonian gravity in this small curvature limit, and one can even give quantum description to Newtonian gravity in terms of graviton exchange. That has been realized in recent years. But then the question still remained how to show the quantum mechanical nature of gravity. And these studies people have been so far pursuing and are pursuing through cosmological observations, gravitational wave detection, but so far there has been no signature. Now, recent years, people are trying to see whether at a laboratory scale or tabletop experiments one can test. This is the idea that was proposed in 2017 by the group in University College London, Shogoto Bosch and his group, about using gravitationally induced entanglement involving massive objects, where you produce each object in a spatial superposition of macroscopically distinct states. So this kind of experimental arrangement with two adjacent Stern-Gerlach type or other interferometers, where you have macroscopically distinct states and large masses involved. And we had recently our paper, our proposal of also detecting quantumness of gravity through a complementary arrangement, where you try to detect whether if the measurement of gravitational field affects the subsequent properties of the system being measured. This is what we call the quantum measurement-induced disturbance when gravitationally field is measured. If such a disturbance is detected, that would also indicate the quantum nature of the gravitational field. As I emphasize, the classical theory model, if gravitational field were classical, its measurement cannot induce any disturbance. That is the hallmark of the classical world I outlined earlier. But the important point for the purpose of this paper is that superposition of macroscopically distinct states, spatial states of a massive object are involved in all such schemes. So one has to first assume the validity of quantum mechanics for massive objects for this macroscopic distinct superposition. Now, how can one then verify it? One has to first verify this initial step to go for the next step of such experimental test of quantumness of gravity. Now, to come back to Leggett-Garg inequality, we have already said, so I shall take just 10 more minutes, I hope. Mr. Chairman, 10 more minutes, okay. We are considering a single time evolving system, and say successive measurements are being measured, and these are the two key assumptions used in deriving Leggett-Garg inequality. And what is important, this assumption, non-invasive measurability, to ensure that this assumption holds good, say we in the classically, Leggett suggested the method of using negative result measurement. I shall explain quickly what negative result measurement is. But the important point to make is that if you use negative result measurement to verify Leggett-Garg inequality, then non-invasive measurability can be argued as a consequence of realism. If you assume realism, if in a negative result measurement, this is guaranteed. If this is guaranteed classically, then the inequality, testable inequality derived from these two conjunct assumptions, if it is violated, its violation has to be attributed to the violation of realism. You see, realism plus non-invasive measurability leads to LGI. So LGI violation will imply violation of both or either of them. Like Bell implies locality or realism or realism. But in the case of LGI, there is an added twist that NIM can be ensured to be satisfied by using what is called negative result measurement. Thus, empirical test of LGI has the potentiality of testing realism per se in itself. So that is one very fundamental conceptual significance of LGI in terms of negative result measurement. Now, what is a negative result measurement? The example we are considering is a particle oscillating between two regions. Now, and the Leggett-Garg inequality simply means correlations between the properties of the particle at two different instances. Now, to simplify the problem, I'm considering that this region over which the particle is oscillating is divided into two parts, and you make a measurement at an initial time by shining a light, which is denoted by this green shaded region, by shining a light whether the particle is in this region or not. If no interaction occurs, if the probe is not scattered, you will infer the particle is here. This is called negative result. The particle is said to interact only if the particle is, say, in region 1. No interactions, you infer it to be region 2. We are considering a two-state, the observable Q plus 1 and minus 1. So the absence of interaction leaves the system classically disturbed. And then you make a subsequent measurement. And in making subsequent measurement, you can shine light in both the halves and obtain the property of finding the particle, which half it is in at that instant. In this way, you can construct the two-time correlations. So what does it mean that, so we are assuming here that if a system is in a state corresponding to the value Q plus 1, then its behavior cannot be classically affected by measuring device, which is activated only when Q is equal to minus 1. This is the idea of it. So I'm not going into further details. So that's why using this idea of negative result, if experiment is done, it will be a strict test of local realism per se. Now, the Leggett-Garg inequality has the main significance of Leggett-Garg comes from testing macroscopic superposition for macro systems, but still for microsystem, it has acquired special significance over the last decade for certifying non-classicality in a device-independent way for a temporal evolving single system, because it is a statistical test, and so it can be used as a tool for various information theoretical applications for certifying irreducible non-classicality, essential non-classicality, as well as for proving deeper foundational issues like even testing realism, because so far there has been no direct test of realism for even microphysical systems. And there are applications of Leggett-Garg for microsystems that are emerging. Our recent work showing how Leggett-Garg inequality can be used to for the generation of certified randomness using a single systems. It is a theory experiment work. Also possibility of using Leggett-Garg for cryptographic constant, cryptographic purpose. Also Leggett-Garg inequality applied to oscillating kaon and neutrinos in particle physics has provided insights into CP violation, measurability of CP violation, the way CP violation present in kaonic oscillation can affect the violation of Leggett-Garg inequality, and its violation can be used as a detection of CP violation or not. In the neutrino case, neutrino mixing parameter, and also application for large spin. This is just to indicate to you how even for microsystems Leggett-Garg is becoming important. And so far these are the kind of experiments that have been performed, but since my time is short, but I can only remark here that for all the systems for which the Leggett-Garg has been studied so far, and the studies on Leggett-Garg have been picking up over the last decade. You notice earlier it was not so much studied, as I had earlier mentioned, and I shall not go into the details of any. Among these are the three most significant experiments, and I can comment on them if there is a question. But the point for the remaining part of my talk is important to note is that so far quantum interferometric tests for massive systems have reached only up to 10 to the power 5 atomic mass unit, and also they do not test macrorealism. These are the atomic and molecular interferometric test large atoms. So this is an important gap in the literature we have, and mass is the most natural parameter for characterizing macroscopicity, and this is what our work sought to do, to provide a scheme using which for any arbitrary large mass. So I will have 5 minutes more, Mr. Chairman. Okay. Thanks. The system we consider is as a linear harmonic oscillator in our work, and it's a purely the most classical like quantum state, and the measurements I already gave the example shining light on one half of the oscillating particle, that is coarse grained spatial measurement to determine which half the particle is in, and it is implemented using negative result measurement, that means shining light on only one, collecting the outcomes for which you get no scattering from the particle, no interaction. And this way you construct two-time correlation functions, and these are the two-time Leggett-Garg inequality, and it's another version that is known as no disturbance condition. And the novelty of our scheme is that while in other uses of Leggett-Garg inequality earlier, same observable was considered to be measured at successive instants, in our case we choose two different observables at successive instance. In the first instant measurement, you divide the region into two halves in a certain way, and for the second measurement, you change the way the regions are divided, which corresponds to the measurement of a different projective operator. These are all projective measurements that is being used. Then I cannot go into further details. Here is how the two-time Leggett LGI look like. But the important point is that the derivations do not require the same observable to be measured at different times. And this is the twist we provide. Moreover, two-time LGI has not been used earlier much, two-time, but it has usually people use three-time LGI or so on. But this has turned out to be a powerful tool in the context of our example. I'm not going into explaining how it is derived. These are the two key assumptions used. And then, in a Schrödinger's pendulum experiment, the non-invasive is implemented by shining light on only one region, and so on. So I managed to convey to you all. I've got further times to explain further details, but this is the kind of results that are predicted. just this is the kind of results that are predicted. The violation of this gives the violation of one version of LGI. This is another version of LGI, the 2-time LGI, and this is 2-time NDC, no disturbance condition. This is a variant of LGI, may be viewed as. And important is that for any value of mass, initial peak momentum and angular frequency, the magnitude of violation remains the same. So it is achievable quantum violations of under the conditions we have specified in our example. It is independent of mass, initial momentum and angular frequency. So it gives a lot of freedom to choose these parameters in a way to demonstrate the desired violation and go up to, in principle, for any large mass we like. In principle, although it is for any large mass we can go, but with the current and near future technology, it seems implementable with the levitated nano objects, which is of the order of this mass, which is about 1 trillion times heavier than hydrogen atom. And of course, there are also oscillating LIGO mirrors, that is the mirrors, LIGO mirrors used in gravitational wave detection experiments that are also potential candidates, because recent technology has improved a lot to achieve ground state cooling and other things. Because a fundamental requirement is for this kind of experiment is to minimize decoherence and noise. For this purpose, the independence of these parameters of oscillator frequency, initial momentum helps, and also the cryogenic technology that has been rapidly advancing. For example, all these objects, levitated nanodiamond crystals of this mass, they've been all been cryogenically cooled to temperature of the order of nanokelvin, millikelvin, where decoherence can be minimized and appropriate low noise tracks. So I better stop now, and questions are welcome depending upon the time. And we have been working in this area over the last decade, and these are the useful review articles. And finally, I end by, this is a comment on our proposal given in the article on our work published in Physics World, that our scheme requires designing an appropriate control experiment to determine the amount of whatever classical disturbance. Although we are claiming negative result measurement by shining light on one half in an as precise way possible, still for such fundamentally important experiment, it is necessary to also have an appropriate control experiment, which we are now trying to design, which can measure the amount of whatever classical disturbance that occurs. And more importantly, we are also trying now to quantify not only the classical invasiveness in such measurements, but also to enhance the macro quantum effect in our example by using quantum Zeno effect, which involves inhibition of dynamical evolution of a system due to repeated measurements. And quantum Zeno effect has so far been verified only for microphysical systems. For macrophysical system, it is an exciting new area which we are exploring, and that can be used also in the context of pendulum experiment. So this is the final comment. All this research enterprise, you may say, what is the expected outcome? The expected outcome is that we may constrain, which I already mentioned, all various approaches that are being proposed for addressing the quantum measurement problem. We may be able to impose not only empirical constraints on them, may rule out some of them. We may also once this quantumness at this level is verified for the kind of massive systems we are considering, that can be used for testing the quantumness of gravity using the schemes I already mentioned, the laboratory-based experiments. because for that it is necessary that a quantumness be verified for those large masses, which seem to be possible with the current technology and is being pursued at the laboratory at the University of Southampton by Professor Henry Coolbrith et al. But there is also the possibility that there, as John Bell had mentioned, we may also find some soft spot where quantum mechanics is actually wrong. So I may end in this way. Thanking you all with this. Question.
With the questions.
Question. So, please read out the question. Please read out the question so that it's
any upper limit of mass where quantumness can be explored.
At the with
upper
the
limit of
no, there is in principle. Yes, in what our scheme indicates that in principle there is no upper limit. That is the importance of our scheme. That it showed that in principle one can think of an experiment. It may be a Gedanken experiment. Like you see, for studying foundational questions in the initial phase of quantum mechanics, these Gedanken experiments played a very important role. Thought experiments. Similarly, now in the next phase of quantum mechanics, these thought experiments. So in that context, our Schrodinger pendulum experiment shows there is no upper limit in principle. But with the feasible technology now and with the systems available, what is exciting is that this scheme is implementable up to 1 trillion times heavier than hydrogen atom. And that mass scale is already quite significant in testing some of the approaches proposed for addressing the quantum mechanics problem, as well as will be useful for testing quantumness of gravity. And that experiment, that is the fascinating development of new technologies of levitated nano objects and the kind of technologies developed for gravitational wave detectors. The mirrors, the oscillating systems developed there 10 kg, which have been cooled to ground state at cryogenic temperature. This is a fantastic technological achievement. So that opens up the prospect of showing quantumness even at the level of 10 kilograms.
Okay,
so this is the new vistas that are now opening up in the coming years as we celebrate 100 years of quantum mechanics.
Okay, sir. Thank you.
Hello, Dipankar, I have a very question, silly question.
Please feel free to ask, provided the chairman permits.
Okay. So usually in quantum, actually, if we calculate these two-time correlation functions, then in general they come out to be a complex number because these two-time measurements, they are not Hermitian in general. So usually we make it symmetrize the combination of these two-time operators, and then we obtain the real numbers actually. So in quantum mechanics, do we need some explanation for that type of two-time measurement operators which are not Hermitian?
Yes, so that is a very good question. Another, because that also is related to quantum measurement description, because the measurement I discussed, the standard framework for describing measurement, von Neumann type framework, is for operators which have orthonormal eigenstates. You see, so it is geared for Hermitian operators in a way. But because the founding fathers of quantum mechanics thought that quantum mechanics should only describe Hermitian observables, because Hermitian operators have real eigenvalues and so on. But that is not a very strong reason, even imaginary.
Yes, because here somehow these two-time measurements where we are going beyond that formalism, I think. Because here, in many cases you can have this. Actually, we tested for simple two-level system and doing measurement at different time, and most of the time you will come out with non-Hermitian operators.
Now for that you need enlarging the quantum measurement theory to deal with how quantum mechanics can describe actual non-Hermitian observables. And it is in this context the more serious question is that after all these 100 years of quantum mechanics, now very important, how does we actually, that's a very of usual observable, the time distributions, because you have the arrival time distributions with measurable quantities, transit time. These are all measurable, but quantum mechanics
does not give you the prescription.
Yes, apart from measurement problem, that is, I say, the most serious technical problem of the quantum formalism. And already many of you may have followed in the archives, there have been various proposals for operators for time in the quantum mechanics, how what arrival time distributions can be described. We had studied this problem way back 20s, but now it is becoming very important. And so there are scheme proposed. There have been a number of schemes, including that by Carlo Rovelli, of a scheme that has been proposed. How do you describe quantum arrival time distributions? And Carlo Rovelli's scheme involves non-Hermitian operator. But then the question comes, can we test those predictions? So that is a challenging area. Already people are working like Siddhant Das in Munich. He has some interesting experiment, proposals for experiment, with whom I am also working. And if such experiments are done, that would be something that quantum mechanics has not been proved wrong in the area where it has been applied, but has been proved to be empirically incomplete. That will be the demonstration of empirical incompleteness of quantum mechanics and verifying some prediction beyond standard quantum mechanics.
Yeah, somehow it has to be extended. Yeah.
That would be the next step, also another exciting breakthrough. So I thought in today's talk, while we celebrate 100 years this month, let us not only talk about the past, but about the future and what exciting things may be in store for us regarding foundational aspects of quantum mechanics. Of course, quantum technology is now, there are so many interesting.
One small question, if you don't mind.
No question. I'm most welcome. And criticisms are most welcome. Skepticism is most welcome.
Okay, sir. But we always say that a measurement is complete only when we reach the classical apparatus stage. So whatever you are describing, they are only the intermediate steps. Ultimately, we have to connect with a classical and apparatus, then only we can say the measurement is complete. Do you agree? Or what is your comment on that?
Yes, and in fact, that is the one of aspect of the measurement. At what point in the measurement process you can consider the measurement to be complete? Can we specify that within quantum mechanics? At what stage is the measurement? What do we mean by? Because the problem in quantum mechanics, as John Bell beautifully said, that what we actually measured has no correspondence within quantum mechanics. As I say, the measurement outcome, we use the word outcome, say a position in the computer screen, a dot on the Stern-Gerlach apparatus, a position. But it should have a theoretical correspondence within the equations of quantum mechanics. That is what this nonlinear modification of Schrödinger equation approaches tries to do, that you introduce a modification to the Schrödinger equation and introduce the assumption of preferred basis, that it is only in the position basis that the measurement outcomes are finally recorded. Then can you describe the occurrence of the outcome and where the measurement process is completed and specify some time at which the measurement is completed. This is the prediction from those nonlinear modification, those approaches. Well, to try to understand, reply to the question you're posing within the quantum mechanical, not within the quantum mechanical framework, but by extending it so that one can give an empirically verifiable prediction at which stage the measurement is completed.
Thank you.
Okay, if no more questions, we can thank sir. Thank you very much, Dipankar sir.
Who posed it is a very, I would have loved to say more about it, but you may contact me over email or whatever, or if you later have time. Okay. It's a very important question.